today we're going to be reviewing the paper Can We Focus by Diego Blas, Vitor Cardoso, and Jose María Ezquiaga. It's a short paper, shouldn't take too long to get through, but it'll at least be interesting. It's about gravitational lensing and black hole formation. Note that this is about Kugelblitze. So these are the formation of gravitational or of black holes via incoming electromagnetic radiation. Now, we already know that those things aren't really possible to make because of quantum mechanics, at least on a normal scale. However, it's interesting to think, could this even be possible without quantum mechanics using gravitational lensing to focus electromagnetic waves? So we're going to find that out. So let's start with the abstract. And let's just get started. So black holes are extreme outcomes of general relativity and can form through a variety of ways, including gravitational collapse of massive stars or quantum fluctuations in the early universe. Here we ask the question of whether they can form via focusing of radiation, that's electromagnetic waves, by compact binaries or intense lasers, or via trapping at the light ring of black holes. We provide evidence that gravitational lensing of radiation from a small, finite number of sources is not a viable mechanism to form black holes. Okay, perhaps very unsurprising, black holes are not easy to make. But let's see how they do it. It's only a few pages. Let's see what they do. They have a nice diagram too. All right, let's zoom in so we can get a better look here. Oh, by the way, if anybody's interested in reading this paper themselves, if they want to go back at it for whatever reason, just type in this number over here. If you guys can see it. Type in that number into Google. This was posted about a week ago, so that's where you want to go. Right, let's jump in. I think everybody should be able to see this. Let me just pop this out really quick. Make sure that it's... Yeah, okay, good. So, let's put this over here for now. Black holes are an essential solution and an inescapable conclusion of stellar collapse in general relativity. I think we all hopefully know that. Besides stars, which ran out of nuclear fuel, that's the very first way that we figured out that black holes would form. You basically have a star that runs out of fuel. It's so big that it collapses in on itself and it forms a black hole. Alternative mechanisms to form black holes include trans-Planckian energy collisions or fluctuations in the primordial universe. I don't know what a trans-Planckian energy collision is, but I think I can probably infer it. But it doesn't seem particularly relevant, so let's just keep reading. Difficulties, mostly related to pair creation, in creating black holes from light have recently been studied. In fact, this is one of the papers that we looked at quite recently. Alvarez Dominguez, Guerre, Martin Martinez, and Paula Gomez. That's the paper that I made a video about, actually. In fact, it's quite hard to make black holes using electromagnetic radiation. Right, so these difficulties in creating black holes from light have been recently studied, recovering a decades-old discussion on the existence and stability of geons. Geons are just another word for black holes forming from electromagnetic radiation. Here, we entertain an alternative production mechanism to form black holes, through the focusing and collapse of radiation. Okay, a possible mechanism to produce black holes, see figure 1 for a depiction, might consist of a system of lenses, regardless of their nature. These are gravitational lenses, by the way, that would focus radiation to the point where it would collapse to a black hole. So let's take a look at this figure. So in this figure, they have a source here, lenses. They focus it so much that you get a black hole. Maybe that's possible. Who knows? That's what they're trying to investigate. And these are presumably going to be gravitational lensing. So this is just a schematic. Did they follow your recipe? No, they probably didn't. Remember, energy and mass are just two different forms of the same thing in general relativity, or in special relativity as well. And so as long as you focus enough energy into one place via electromagnetic radiation, then it's totally possible that you can collapse it to form a black hole. That's the whole question. So that's what they're studying. Right. Right. For example, take two weak beams of light, focus each appropriately such that the power per unit area is sufficiently large, and collide them. So you have two beams coming in, they're both focusing in, and they collide at a point. Would this result in a black hole? Alternatively, shine a light onto a black hole, which is itself a gravitational lens, and wait for radiation to pile up at the light ring. The light ring is the region of space around which light orbits. So light can orbit black holes, And so that's what they're talking about here, the light ring. Will one get mini black holes forming at the light ring? Because you can just pile up more and more gravitational or more and more electromagnetic radiation in the light ring, and so eventually you'd have a lot of energy in the light ring. We wish to show here that neither of these outcomes is likely to occur if the radiation is emitted by a finite and small number of sources. The term small will be characterized in the main text. Great. Let's zoom over. So, next section, let's see what they have to say. Can we focus radiation to produce a black hole? We are concerned with possible black hole formation through the lensing of gravitational, electromagnetic, or any massless waves somewhere in the cosmos. So actually, they're not just using electromagnetic waves, they're using gravitational waves as well. There are other massless waves, or in principle there could be other massless waves, but we haven't seen any. So there's gravitational waves and electromagnetic waves. That's what they're going to be looking at. And you can lens these basically in any way you want. You could use gravitational lensing, you could use optical lensing for light. We will use the hoop conjecture as a discriminator for black hole formation. I'm not familiar with the hoop conjecture. However, I have a feeling that they're about to explain it. When a system of mass m, in d equals 4 dimensions, we live in a 4-dimensional spacetime, gets compacted into a region whose circumference in every direction has a radius less than or equal to the 2gm over c squared, a horizon, and thus a black hole forms. Here g is Newton's constant and c is the speed of light in a vacuum. So what they're saying here is that basically if you can fit that energy or that mass into a volume that is, or into a region that is smaller than the Schwarzschild radius for that same amount of mass, then it will form a black hole, which is reasonable. I mean, perhaps there are other ways to form black holes, but as far as we know, like if you take a whole bunch of mass and you put in it, or a whole bunch of energy and put it in the small of space, it'll form a black hole. And this is what the hoop conjecture is about. Basically, if you can fit a hoop of size equal to the Schwarzschild radius of a black hole of equivalent mass around the mass that you're interested in, you have a black hole. In particular, take a single violent process producing a large amount of radiation. Can we lens it by a black hole or star or any human-made device to focus radiation to such an extent that a black hole is formed? For a single violent process, I suspect not, but maybe you can. A study of exact solutions of Einstein's equations describing impulsive waves just meaning a large burst, and that like a very short, very large burst of energy, essentially. What's the Schwarzschild radius? The Schwarzschild radius, that's what this number is. So you take Newton's constant g, you take the mass m, you multiply it by 2 and divide it by the speed of light squared. That is the size of a black hole for a given amount of mass. So if you can fit that amount of mass into a region smaller than that, then you'll have a black hole. Right. That's what the Schwarzschild radius is. Right. So if you study the exact solutions of Einstein's equations for impulsive waves, apparently you find that parallel light beams don't attract. Okay, so if you shoot two beams of light parallel to each other, and they're very, very bright, very, very strong light, they actually don't gravitationally attract each other, which is interesting. I didn't know that. I'm actually going to pull up that reference and read it later, because that's fascinating. I would have expected that they would have. How does G know where the center is? I don't know what that question means. Hence, simply smoothly self-focusing a single beam of radiation is unlikely to produce collapse. So the conjecture here, the claim here, is that if you just have a single beam of radiation, because it doesn't self-attract, because two beams of radiation don't attract each other, a single beam of radiation won't attract itself. And so what you'll end up with is it won't be able to form a black hole. It's just a beam of light, and so it's not going to collapse in on itself. So that's what they're claiming here. It seems plausible to me. We therefore require two such beams to collide. So you're going to have two beams come at each other and overlap, and then you can have a certain amount of energy density there. The hoop conjecture applies well when the object being hooped, meaning you're drawing a circle around it, is at rest, in this case the final black hole. So we consider two equal beams colliding head-on. So you just have two beams, they're going to collide, and they're going to overlap, and where they overlap is where you're going to have this energy density. This scenario could describe, for instance, radiation from a binary coalescence being lensed by a supermassive black hole. or a neutron star and a black hole formation could occur at the focal point. So imagine that you have a, imagine you have, say, two binary coalescence. So you have two mods, or not mods, two stars orbiting each other, and then they're eventually going to merge, and then two more stars orbiting each other, and then they're going to merge. Then you have a supermassive black hole in the middle, or two supermassive black holes that are focusing the gravitational radiation that's coming from either side until they collide in the middle. That's the idea. We consider a setup where the radiation from a binary coalescence, say, is focused by a system of lenses and then made to overlap with a similar focused beam from another binary. Let's see what this footnote says. Lagging. Alternatively, radiation from a single source could be split into n components, each of which can be focused and made to overlap with the other in an attempt to produce black holes. Okay, yeah, so the idea is you basically just need to have two beams. It doesn't matter how many sources you have. In other words, we assume that we are technologically sophisticated enough that we can capture the radiation emitted by a binary coalescence, emitted to all portions of the sky, and convert it to into a nearly plane-fronted beam of radiation. Yeah, so this is obviously in the realm of sci-fi, but it's an interesting thought experiment and an interesting calculation to do. This beam will be assumed to be of high frequency. We make this choice to so if you have high frequency radiation, then you don't have to deal with like diffraction, and so you can just use classical optics. So we're going to have high frequency radiation, and then you also have a cross-sectional area of A, so we're going to use the variable A to represent the cross-sectional area, and an intensity, energy per square meter per second. So this is, you have a certain amount of wave, like this is the radiation, passing through a given area. So it passes through the area, and then you have a certain amount of energy per second passing through that area. That's how you measure intensity, and we're going to use I for that. So we assume that a system of lenses is placed properly to focus it to intensity I tilde. Sorry, one sec. People are being annoying in chat. We assume that a system of lenses is placed properly to focus it to intensity I tilde. So the intensity is going to go up, the cross-sectional area will go down. And because of energy conservation, it must follow that if the intensity goes up by a certain amount, the cross-sectional area must go down by the same amount. So we have this relationship here. And the footnote says, or more specifically, conservation of phase space volume, which is, it's fine. So we have IA, so intensity times area times cross-sectional area is equal to the new intensity times the new cross-sectional area. That's all. And that's all they're saying. The mass density in such a beam, well, to find the density of such a beam, let's think about this for a minute. So we have let's think about units. Energy is conserved here. It's just this isn't quite energy conservation. This is like mass. This is like energy flux conservation, basically. So we have cross-sectional area times intensity. So that is the amount of energy flowing through, the amount of energy per second being pushed through by this beam. And then we're dividing it by an area. And then we're dividing it by C. Why are we dividing it by C? Why are we dividing it by the area? The mass density should just be the energy density divided by the speed of light squared, because E equals mc squared. So we just need to figure out the energy. To figure out the energy in a beam, well, if you have the intensity, the energy density divided by the speed of light. Yeah, so it's an intensity divided by the speed of light will give you energy density, assuming that the thing is moving at the speed of light. Roughly the reason for this, I don't know why they wrote it this way, it's just I over C. So energy density times the speed of light will get you to, so you have a certain amount of energy, and then you know the speed at which it's moving, that will get you to the rate at which energy is being transferred, which is what intensity is. So I don't know why they have IA over AC, it should just be I over C. So this is the energy density here, this formula. The A's cancel out. I don't know why they're doing that, but the A's do cancel out. And then so that's energy density, and then they divide by c squared, because this is E, because you have E equals mc squared, so you divide by c squared to get m, and so you get the mass density. Mass density is just the intensity divided by the speed of light cubed. Now, we take one such beam with this much mass density and collide it with its equal. So you're gonna have two equal beams. They're gonna collide with each other, and so you're gonna have twice the mass density. The overlapping region has length L in all directions, such that A is approximately L squared. Now, this statement here, A tilde is approximately L squared tilde. This is a statement about how you can focus beams. So, roughly speaking, the length of the smallest, the length of the focal point, because the focal point is not actually a point, right? The focal point is related to the cross-sectional area. And so the overlapping size of that focal point is approximately equal to the cross-sectional area of that focal point. So that's roughly that's the statement that's being made here. The hoop conjecture requires that for a black hole to form. So for a black hole to form, you have to have this as true. So Dan's thesis was on gamma-gamma interaction. That's fun. Okay, so this is the hoop conjecture. So in order for a black hole to form, we need to have that the Schwarzschild radius of this mass density, or of this volume with a certain amount of mass in it, in the form of radiation, is what am I trying to say? In order for the hoop conjecture to be satisfied, and thus for a black hole to form, it must be the case that the mass inside a region, that the mass occupies a smaller region than the equivalent Schwarzschild radius for that amount of mass. And so 2gm over c squared is precisely the wait, did they miss a 2? Oh, no, never mind. The 2 should be in the numerator. That's fine. So 2gm over c squared, that's what this is, 2gm over c squared. That's the Schwarzschild radius. And so what they're saying is that the Schwarzschild radius has to be bigger than L. Why are they saying it has to be bigger than L? Oh, L is roughly the size of the region. Okay, yeah, no, that's fine. So L is roughly the size of the region. So they're just saying that L, which is roughly the length scale of the region that has this overlapping energy in it, that has to be smaller than the Schwarzschild radius. Yeah, it's the characteristic length. Bingo. So this must be true in order for a black hole to form. And m inside is the mass within the cube of volume L cubed, and the mass inside then is just twice the radiation energy, or the radiation mass density times the length cubed. So it's twice because you have two overlapping beams. The length cubed is because you have a cube of volume L of side length L, and then a rho is just the mass density. And they put a tilde on it because it's the focused mass density. So they can substitute in rho. Rho is just I tilde over c squared. L tilde is just, or L cubed. L tilde cubed, they're not replacing at all. And so then you have C is 4g over c to the 5th power times I tilde L tilde squared. This seems, does this check out units? Do the units work out here? So rho is I over c squared. Oh, no, this is just correct. Yeah, the 2 and the 2 become a 4. The c squared and the c cubed become a c to the 5th. The I becomes an I tilde, and then you have an L cubed and an L in the denominator, giving you L squared. So this is C, and this has to be greater than or equal to 1 in order for a black hole to form. And it happens to be the case that because L squared is approximately A, we have an L squared here, we get an A squared, and then we have I, remember that I tilde A tilde is equal to IA, we can replace this bit with IA. So, this is a nice formula. It tells you that if you have it, you can't hear me? Did my audio kick out? Testing? Oh, Okay. Liar. Liar. Somebody lied. Okay, fine. So this is basically, this is a number that has to be bigger than 1 if you want a black hole to form. And now this is just the size of the initial beam. This is the intensity of the initial beam, and these are just constants. So note that the conclusion above is not simply a statement about energy conservation. It depends crucially on the fact that the size of a four-dimensional black hole scales with its mass, embodied in the Hoop conjecture, and on the fact that the luminosity, IA, is a dimensionless quantity in 4 dimensions. Is that true? Luminosity is dimensionless? That's not true. That's not true. That's a mistake. It's almost a dimension. Okay, actually, it's energy per second, which, well, no, it's just not dimensionless. But whatever, it's fine. It doesn't matter. The conclusion may change in higher dimensions where the Hoop conjecture takes on a different form and the maximum luminosity bound ceases to exist or even to make sense. You can absolutely ask questions whenever you want. Why does it have to be bigger than 1? So the Hoop conjecture, which is basically how small do you have to cram mass energy into in order to form a black hole? The Hoop conjecture is just about this statement. You basically have to cram this certain amount of energy into a region smaller than the radius of the Schwarzschild radius. And so the statement here, they write it somewhere. Where do they write this? Yeah, this is the Hoop conjecture, that this thing has to be greater than or equal to 1 in order to form a black hole. Luminosity is dimensionless since it's normalized. They have it as energy per, they have intensity as energy per square meter per second, and then they multiply it by A. So you just get energy per second. So it's just not correct as written, but that's fine. Like, it's energy per second is not unitless. It's okay though. Everything else seems fine. I imagine that the units check out here to make this dimensionally consistent. So yeah, that's why there's a little bit of an issue, and they're not using c equals 1. They're not using the Hoop conjecture is just a formalized version of black hole when. Precisely, it's precisely that. Right. Okay. So they're basically saying that that this conclusion really only works in 4 space-time dimensions. In other numbers of dimensions, you might have a different result. So that's all they're saying here. So, in conclusion, if we want to form a black hole via gravitational lensing of radiation, then the radiation being lensed should satisfy a bound on its luminosity. So this has to be greater than 1, meaning that we can just solve for IA. IA has to be, approximately greater than c to the 5th over 4g. So this is the speed of light to the 5th power divided by 4 times Newton's constant. Cool. Okay, so according to the maximum luminosity conjecture, which I'm not familiar with, but I guess there's a maximum luminosity that you can get from gravitational radiation or something. This is impossible, which is kind of crazy. LIGO Virgo Cagra events have, oh yeah, these are huge luminosities. Yeah, this is huge. So the events, the gravitational wave collisions, or the black hole collisions that produce the gravitational waves that we've measured, produce 4 times 10 to the 5th watts at its peak, which is so much. And that's about 0.1. That is 0.1 rather than 0.25. So this is impossible. Okay. It's certainly not feasible from the lensing of radiation from a black hole binary. Okay, fine. 10 to the 50. 10 to the 50 watts. That's actually correct. So you would need roughly, 25 times more energy than this in order for a black hole to be formable. And you would need 2 of them happening at the same time. Sala, this is just standard units. So in standard SI units, the correct statement, the correct Schwarzschild radius is 2gm over c squared. And so you can divide through, or you can just move the r over to one side. So this over here is unitless. 2gm over c squared is in units of distance, and L is also in units of distance. So it's fine. This is unitless, and this is 1. It's totally fine. Can we somehow store the energy of a gravitational wave? Not with current tech. All right, let's keep reading. Note that the analysis above does not contradict in any way the findings of Christodoulou. Christodoulou is a big deal, by the way. Nor those of Choptwick. These authors find collapse to black holes from gravitational focusing, since initial data in the latter is not constrained by any physics and is possibly appropriate to collapsing scenarios. I'd have to read those papers, I can't comment on it, but I guess they're saying that this is actually not a problem. In fact, if we take n sources, a good proxy for the spherically symmetric collapse in reference 25, I see what they're saying, and estimate 6 would be multiplied by n for sufficiently large n, the hoop conjecture would be satisfied of black holes to be formed. So, what they're saying is, if you only have two black hole collisions, then this is impossible. But if you have say 50 of them, this would be multiplied by 25, which means that you actually could satisfy this condition. So if you have a bunch of black holes in a sphere that are all inspiraling, and they inspiral at exactly the same time, and then you focus that all towards the center, then you can form a black hole. So if you have just the right coincidence of black hole collisions, or if you engineer it yourself because you're super advanced technology, then you can do it. Can we shine radiation onto a light ring and produce a black hole? Okay, so the idea is it's going to be very hard to form a black hole via collapsing radiation, even if you lens that radiation. But maybe they're saying, can we just shine a light onto a black hole, and then the light will orbit the black hole, and eventually you can just build up enough light that it forms a bunch of baby black holes? That's a question that we can answer. The above does not take into account radiation recycling. So maybe the radiation can be used over and over again, because the radiation comes by and passes over, but then it comes back, but maybe you could send it back around, right? In particular, equation 1 does not hold true in strong lensing in trapping regions. So equation 1 was this equation 1? Oh yeah, okay. So in those regions, when the space-time geometry is very, very complicated, that's not necessarily going to be true. We now turn our attention to regions where radiation is trapped and passes more than once. So you're going to have radiation coming by and then going around and coming by and going around. The left side of the inequality has units of energy when multiplied by mass. 2gm over c squared has units of length. So look up, like, if we can just double check this. Schwarzschild radius. The Schwarzschild radius is a distance. It's 2gm over c squared. This is in standard units. That has distance of length. That has units of length. So you might be making a mistake, because we have 2gm over c squared that has units of length. Then we have L. Christodoulou. Christodoulou is the name here. All right, let's keep reading. Right, okay, so the question is, in particular, equation 1 does not hold true in our strong lensing trapping regions. We now turn our attention to regions where radiation is trapped and passes more than once. So again, we have light circulating, basically. Light rays with an impact parameter of b crit. So impact parameter is basically how far away from the center of the black hole is the light ray shining. So imagine the light ray, you have a black hole here, light ray comes by, the impact parameter will be that distance. Or, if it comes by over here, the impact parameter would be that distance. It's just a measure of how close the light ray gets to the black hole. In particular, if the impact parameter is this value, and it passes by the black hole at just the right distance, then it actually just enters an orbit around the black hole. Which is exactly what they say. Will orbit a non-spinning black hole indefinitely, performing an infinite number of orbits around the circular null geodesic. Imagine a situation where a non-spinning black hole is being bombarded with radiation from some catastrophic event like the merger of two black holes. So you have a black hole, and then you have radiation coming in all the time from over here, and some of it's going to get caught in this orbit. High-frequency radiation hitting from one hemisphere orbits a large number n times before it encounters radiation hitting from the opposite hemisphere head-on. So you can have this going in both ways. Or you can have it going like this, where they collide. The point is that you can have high-frequency radiation colliding with each other while it's going around the black hole. For radiation to orbit a large number of times, it has to be fine-tuned close to the critical impact parameter. So here they're going to take delta, which is just a small deviation away from the impact parameter. That's going to be 1 minus the actual impact parameter divided by the critical impact parameter. So let's say your impact parameter was like 1% bigger. If the actual impact parameter of the light that's about to hit the black hole is 1% bigger than this impact parameter, if it's 1% bigger than the critical impact parameter, then this delta would be 0.1 because it's 1 minus 1.01 divided by 1, so it'd be negative 0.1. Even with standard units, has the transition from theoretical units to physical reality been addressed? There's no theoretical units being used here. We're just using standard SI units, meters, seconds, joules, kilograms. Nothing, no issue here. Right. Yeah. So by the way, the paper is called Can We Focus? So delta is just the slight deviation away from the impact parameter. Assume it's going to be small. And so if you want it to orbit n times, the amount of times that the light will orbit before it escapes is going to depend on how far away you are from the impact parameter. If you're at the impact parameter, it'll orbit an infinite number of times. If you're slightly away from the impact parameter, it'll orbit a different number of times. And so in particular, if you're slightly less, log, this should be greater. Yeah, if your impact parameter is slightly greater, this doesn't make any sense. I think this should be log of negative delta. Because if your impact parameter is smaller than the critical impact parameter, it should actually fall into the black hole. Whereas if the impact parameter is greater, then delta is negative, and then the log is not defined. It should be negative log of negative delta, I think. But anyway, assuming that they make that correction, that they do it properly, the number of times it orbits around the black hole depends on the logarithm of the deviation from the critical impact parameter. That's what they're trying to convey here. Sorry. These trajectories get close to the light ring. And so you can actually figure out how close they get, apparently, for a given impact parameter delta. So again, for a given impact parameter delta, this is the radius that they get to. So remember, the light ring radius is 3 times the times gm over c squared. This is about 50% further out than the edge of the black hole. So if you take a black hole and you go 50% further out from the edge, that's where the light ring is. And so the place where these not quite perfectly tuned light rays end up is slightly further away than the light ring. So they're just going to make a supposition. Suppose, therefore, that we can make radiation from a system fill the light ring and orbit it for a large number of times, say n. Based on the above scaling, one might suspect that if a black hole forms, it could be sub-Planckian in size, and our classical estimates would not apply. Well, that would be a problem. So no, we're not going to form any microscopic black holes because that would be a problem. Instead, they're going to talk about classical black holes, I assume. But it is easy to show that black holes can never form by filling the light ring. Okay. Take a binary of total mass m sub-binary close to a supermassive black hole of mass m, which will lens the gravitational waves. So you have inspiraling black hole binary, supermassive black hole, so the waves coming off from the inspiraling binary get focused by the supermassive black hole. The total radiation emitted by a binary during its lifetime is about 5% of the mass of the binary. Okay. And it takes a certain amount of time for light to circle around the light ring. I have no idea where this number is coming from. 30 times the light ring radius. Also, that doesn't have units of time. Oh no, it does have units of. It does have units of time. So 30 times the amount of time that it takes to orbit the light ring radius. Where is that number coming from? That should be a 3. That's just a typo. Yeah, that should just be a 3. It shouldn't be 30. it should be 3 for the same reason that there's a 3 here. You're just taking this number and dividing by c squared, or dividing by c. Because if you have the distance that it has to travel, and you divide it by the speed, then that'll give you a time. Yeah, so that's just a typo. So it takes a certain amount of time for light to circle around the light ring. So even if all the radiation is channeled onto the light ring of the supermassive black hole, then what's L? What is L here? Oh, L is the luminosity. Yeah, so what are they doing here? How did they get this? Yeah, I'm curious where this came from. Maybe they'll explain. Let's keep reading. Where we normalize to an optimistic value for radiation to be high frequency, the binary needs to be much smaller than the supermassive black hole. Based on equation 6 with luminosity equals IA, we conclude that we cannot form a black hole in this way. I want to think about this some more because it's not clear to me at all where this formula comes from. Okay. So we know the amount of time it takes to get around a black hole. And so the luminosity is going to be, the longer it takes to get around the black hole, the weaker the luminosity will be. And so you want to divide by the amount of time. I think... Okay. Okay, I see what they're doing. So they're taking a supermassive black hole. They're saying that it has 1,000,000 times less mass than the binary black hole, than the binaries. Well, wait a minute, but then... Yeah, what are they doing here? So the binary needs to be much smaller. That's fine. Okay, so they're not actually going to explain. So the binary needs to be much smaller. So presumably, that's either where the 10 to the 3 is coming from. Oh, they have m binary over m. Oh, I see. Okay, I completely missed the over m. So they have 10 to the 3 times the mass of the binary. What are they doing? So the luminosity is... Okay, let's think about this. Let us think. So, you take the energy from the coalescing black holes. That's this much energy. Now it's going to spread out over... We're going to take all of that and we're going to spread it out over the light ring of the... Yeah, over the light... No, I don't think that they're setting this up for a specific case. So they want to take all of that energy and spread it out over the light ring of a supermassive black hole. So the energy is this much. And, okay. They're just... Luminosity is just energy per second. So they're just dividing the energy by the time. Now, so I think that they've made a mistake, actually. This should be 10 to the minus 3. Or 10, really, it shouldn't even be 10 to the minus 3. It should be like, so they basically put this in the denominator. They have an mg in the denominator, and then they're going to get an extra factor of c to the third in the numerator. And they're basically just saying, well, the mass of the supermassive black hole is really, really big. So we'll call it like 1,000,000 times bigger. So that's the time. And then the energy is mc squared with another number. But it's not clear to me why they have 10 to the 3 here. It should be about 0.05. I don't know why. Maybe, I mean, we can just keep reading. It might just be a mistake. They might have some other justification that they need to fix and explain better. Not super clear to me, but that's fine. Based on equation 6 with the luminosity equals to IA, we conclude that we cannot form a black hole this way. Roughly, you need that L is equal to 4, or c to the 5th over 4g. But here, they have they have 10 to the minus 3rd rather than c to the 5th. Oh, actually, Oh, I'm sorry. Yeah, so what are these factors for? This is just 10 to the minus 3. Why do they do that? No, this isn't a unit issue. I think that it's because of this typo. I think what they did is they took 0.05 and divided it by 30, and they got 10 to the minus 3, roughly. Yeah, okay, that's exactly what happened. They took this 30, which would have belonged down here in the denominator. They took the 0.05, which would have belonged in the numerator. So 0.05 divided by 30 is 0.0167. And they called that 10 to the minus 3. Now, I don't know why they wrote it this way. This is a typo, by the way. That should just be a 3. So it's actually a mistake. It should end up being 10 times bigger. Still very, very far from being able to produce a black hole, because you need a factor of 0.25 rather than a factor of 0.01. But it is a mistake as far as I can tell. Yeah, thus we can thus rule out generic black hole formation from lensing of gravitational waves from standard single astrophysical sources. What about bombarding a black hole constantly with radiation, say the cosmic microwave background radiation? Then effectively, C, this is our hoop parameter. This is n times IA. So A here is this is the area of the surface. The area of the surface centered at the critical impact parameter. So you basically, the critical impact parameter is a number, and then you can just draw a little circle around it, and that's the area of that surface. And n is given in 8. So n is the number of times that the radiation goes around. So basically, you're just taking a whole bunch of radiation and pushing it at a black hole. And we know that there's going to be a certain size that will actually orbit the black hole a certain number of times. And we know how many times each different place along that size will orbit the black hole. And so that's where this formula is coming from. Well, this is just geometry here. This g squared m squared delta squared over c squared. That's the area of the surface centered at the critical impact parameter. And n is that formula that we saw earlier. And then you can just substitute in numbers. We know what a is. We know what n is. N is this. So these both depend on delta, which is the deviation from the critical impact parameter. And so we get a formula. And I guess they're normalizing to the intensity of the cosmic microwave background radiation. And so if you assume I is 1, which is the which would mean that you have, assuming that this fraction is 1. So the cosmic microwave background radiation is 10 to the minus 9 watts per square meter. So if you use the cosmic microwave background radiation, then you get this absurdly tiny number, is what it boils down to. Did they fix the mistake? The mistake shouldn't have carried on over through 12, because it's a different formula. And this is the mass of the black hole. So roughly the idea is that this is not going to happen, because this is a very, 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 very small number. Essentially, you need a huge amount of intensity coming in kind of at random if you want to form black holes. You need like 56 orders of magnitude more intensity than the cosmic microwave background radiation. Or you can increase the size of your supermassive black hole, but that doesn't help that much. And that should be an m squared, by the way. Not just m, that should be an m squared. But that's okay, it's just a typo. So, again, no black hole formation is possible, assuming that delta is much, much less than 1. So, our hopes and dreams have been blown out of the water. Surprise, surprise. But anyway, let's read this conclusion. Our results show how possible black hole formation from ultra-intense lasers is just not a viable or very effective black hole production mechanism, and that in general, the production of trapped surfaces from focusing of radiation will not occur. Our estimates apply to high-frequency radiation. For low frequencies, similar results would apply as their larger wavelengths would prevent more focusing due to diffraction. These findings also echo similar results for fine-tuned initial data concerning high-energy collisions of two black holes, or results showing that black hole formation is accompanied by extreme features. They don't have a period at the end of that sentence. We have not included spin in our arguments as it seems to worsen the situation. Co- and counter-rotating particles would not even collide since the light rings are located at different radii. Yeah, so if you have a spinning black hole that you're trying to form black holes around, then that makes it even worse. So that's the paper. I think it's actually quite interesting. It wasn't so surprising, all things considered. All things considered, I was kind of expecting that it wouldn't work because forming black holes is generally not easy. But it's good to know that black holes won't just spawn orbiting other black holes. That would be kind of worrying. So, one less thing to worry about, I suppose. Overall, I think the paper's quite interesting. There were a few typos, but that's okay. Typos are to be found in preprints. Again, if anybody's interested in reading this themselves, this review will be posted on YouTube. But also, you can read this yourself by looking at this number over here. Or you can just type in the author's name and the title. So, I'm going to open the floor to questions. I'm just going to answer questions from chat for a bit, and then we'll end the live. So, how strong of EM radiation would you need? Well, let's go take a look at the formula. So this 10 to the 56, if you had a supermassive black hole, which is like, a billion times the mass of the sun, then you would get that, you would get 18 factors of, hold on. A is m squared. Yeah, you would get 18, you would get a free 18 power increase here. But then you would still need 38 orders of magnitude more intense than the cosmic microwave background radiation. Or alternatively, you can make delta very big, I guess, which you don't want to do because then you're missing the black hole entirely. So for delta small, you need at least 38 orders of magnitude stronger than the CMB. It's just not going to happen. Well, if that's all we have, by the way, if you guys like this kind of stuff, encourage me to do it. If I find that I can get plenty of support during these lives, I'm more encouraged to do them. So, I have a Cash App in my bio if you care for it. Also, join the Discord. The Discord link is in the link tree in my bio, so it's a really cool thing to do. There's a bunch of people. We can talk about physics, and I'm a lot easier to reach there. We can also talk about politics, religion, etc. Thank you for the spider. I appreciate that. Would these assumptions change if luminosity energy wasn't dimensionless? Yes, they did make that point. That they absolutely made that point that in fewer than 4 dimensions or in more than 4 dimensions, these calculations change entirely. It is okay to compare the magnitude of CMB. Yeah, sure. The CMB has a particular magnitude. We can measure it. We know how intense it is. It's 10 to the minus 9 watts per square meter. That's what it is. Okay, can anyone publish such a paper? So this is a preprint. It's not actually published. It's just on the preprint archive server. But in order to upload such a thing, you do need a university affiliation or you need an endorsement from somebody who's religious or who's university affiliated. So it's not the easiest thing to do if you're not already in academia. But is 38 orders of magnitude bigger than the CMB actually that big? Yes, it is. That is 29 watts per square meter. So let's go look up most intense laser intensity. So that's 6 orders of magnitude than the most intense laser we've ever produced, and you would basically have to bathe the black hole you'd have to bathe the supermassive black hole in a laser that is that intense everywhere. So yes, it is very, very big. So it's like we could feasibly get to that intensity. We could feasibly get there. This per cubic centimeter. Oh. Yeah, okay, this is way more intense. Yeah, so still. We could in principle get there with lasers. However, those lasers are very, very small. And so if you want to bathe a black hole in that intensity light, you have to have trillions or quadrillions or whatever of these lasers all lined up to bathe the black hole, right? Because these are supermassive black holes. They're not small. How is this different than a Kugelblitz? It is a Kugelblitz. We're making Kugelblitze. Bingo. That's what they're saying is impossible in this case. All right, y'all. I'm going to end the live because I want to fill up my water. But I will catch you guys tomorrow for the normal debates. And I'll see you guys then. This will be on YouTube. Take care.